last day about methods of measuring rate. Solids and liquids. Thank you so much. Do solids and liquids have concentrations? Can you measure the concentration of a solid in moles per liter? No, because literally moles per liter means moles per liter of solution. Is a solid a solution? No, although you can have alloys, but those are a different thing and we will not be dealing with those in grade 12, okay? So solids and liquids do not have concentrations. Remember, COC, CONC with a little n at the top is concentration. Why? I keep spelling it wrong. Concentration is concentration. Okay, do not have concentrations. Therefore, you cannot measure a change in concentration. You can't change the number of particles per liter, right? It's just a set value.
I would also add like that they're actually considered like fixed.
They are fixed, but we don't consider a concentration as much as we do a density, right? So we just kind of leave that aside. Yeah?
So a liquid just pure something. So if you mix it with something, it gets fixed.
If you mix it with something, it does have a concentration, but we won't be dealing with that this year. So I'm just going to say, to make your life easy, solids don't have concentration, liquids don't have concentration, so you cannot measure a change in concentration. Technically, can you have an alloy that's a mixture of gold and silver and have different proportions? Yes, you can. But are we dealing with that this year? No, we're not. So let's not even think about those things because they will just make our life more complicated. Okay? Yeah. All right, so we were asked about these ones. Indicate two methods for determining the rate of each of the following reactions. So you could say, if I have a solid, what can I do with a solid? I could measure a change in mass of copper over change in time. Are there any other solids I could do?
So silver is solid.
I could do silver, sure. I could do a change in mass of Ag, solid over change in time. Now I have some aqueous stuff. I have silver nitrate and I have copper nitrate. Would I say change in concentration of AgNO3? Probably not. Remember, when you're doing these, it is best to look at them as ionic equations. Yeah? So you would actually be looking at 2Ag plus NO3 minus, 2NO3 minus, and Cu2 plus 2 NO3 minus. And so you would say, NO3 minus is our spectator. So we could measure a change in the concentration of Ag plus over a change in time. We could measure a change in the concentration of Cu2 plus over a change in time. You could also say, if you wanted to, you could say we could measure a change in color. over a change in time, which we could then convert into copper over time. Yeah? So which of these would probably be the easiest choice?
And just all
Probably, I would say this is a really good choice here because color is easy to measure using the color measurer called a colorimeter or a spectrophotometer if you want the real names. Copper mass is not bad as long as it's, the limiting reactant. So you could do it that way. This one is less easy. But if you were asked to list a method, I couldn't say you're wrong. You could titrate the silver at the beginning and you could titrate the silver at the end, and that would be okay. Yeah? How about B? It's all gases. Okay. So we could measure a change in volume. We could measure a change in pressure. We could measure a change in, can't do mass of the system because it's all gas.
Sure.
So if it is all gas, we cannot do a change in the mass of the system, because if we had an open system, which is required for the system to change mass, then all the reactants would escape and you wouldn't be able to measure anything. Yes, it would all just be like over there and over there and over there, making it impossible to measure. Okay? All gas systems must be closed. So if it's all gas, must be a closed system. Otherwise you can't measure anything. So those would be the two for that one. Or, there's another one. Color, change in color over change in time. I see lots of people writing things. Were we not getting them? Were we mostly getting them? Just need a few details. All right, how about C?
Well, here, mass of the system.
Mass of system, because we have a gas.
Volume of the gas.
Change in volume, CO2. Change in time. Change in pressure over change in time.
You can get an open system.
What's that?
Open system.
This would have to be an open system. This would have to be closed, but you'd have to have like a movable, something movable. And this would have to be closed. Calcium carbonate is a powdery white solid. Calcium oxide is a powdery white solid. Would we like to measure the mass of either of those powdery white solids? Could you tell which one is which? Probably not. So I would say that these three are the best choices. If I was to give this to you, I should probably list in there that those are both powdery white solids. I'm going to say that I need to fix this. Don't put that down. This is for me. Powdery white solid. Powdery white solid. So you couldn't tell whether you had calcium carbonate or calcium oxide. How much was this? How much was that? You'd be like, So that would be really hard to measure. Okay? And And our last one here. We have a solid, so we could measure a change in mass of BaSO4 over change in time.
Concentration as well.
We could measure a change in concentration of what?
H2CO4 and barium MnSO4. Oh, sorry, but barium OH2. For C, like in both two.
Sorry, for C?
For C, since they're solid, we can't measure by mass.
I would say we would not want to measure the masses of the solid because they're both powdery white solids. But since I did not tell you that, you might have answered that way. Do you know what I mean? That's why I've told myself I need to fix that question. So for this one, remember, you need to do the net ionic equation and the complete ionic equation. So this would become 2H plus SO4, 2 minus plus Ba, 2 plus 2OH minus goes to BaSO4 solid plus 2H2O liquid, and everything back here is aqueous. So you could measure a change in the concentration of H plus, or you could measure a change in the concentration of H plus. What else could you do? You could do SO4 because it's aqueous. You could measure change in the concentration of barium. Anything that's aqueous. So our other one would be change in the concentration of hydroxide. Aqueous, aqueous. Do I love any of those? No, but I would give you credit for them, okay? The reason I don't love them is that barium and sulfate are hard to measure. Yes? Barium and hydroxide, are they together in solution? Like say the concentration BaOH2. Are they actually together when they're in solution? Or are they separate? If they are aqueous, they are dissociated. Okay, and since it says aqueous, they must be dissociated. Okay, so you need to list them separately. For this one, to be honest with you, this one, I think the easiest way to do this one would be a conductivity meter.
Huge.
Conductivity meter measures a change in the conductivity of the solution. We start with 1, 2, 3, 4, 5, 6 ions in the reactants. We finish with 0 ions in the products. What's going to happen to the conductivity as time goes on? Will it increase or decrease? Tell your partner.
There's like no ions. That means there's no charge. Which conductivity is gone. So far, I've been rude.
Or stay the same. So you could vote increase, decrease, stay the same. Are we ready? 5, 4, 3, 2, go. Yeah, it's going to, I've got mostly decreases. It's going to decrease because what conducts electricity in solution? Ions conduct electricity in solution. If you imagine, here's a metal, yes? I got a little paper clip here, yeah? And I got a beaker here. Not a very clean beaker, but it's a beaker. Actually, I'm going to use the clean beaker. Why would I not use the clean beaker? That's daft, isn't it? Is that metal in solution? Yeah. No, it is not dissolved, right? Paperclip is still sitting there. So you can't have a metal in solution. You can have metal ions in solution. You can have non-metal ions in solution. You can have polyatomic ions in solution, but you cannot have a metal in solution unless it is dissolved in another metal, in which case that would be an alloy, but we're not talking about those in grade 12, so let's pretend I said nothing about that, okay? Did that make sense?
Yeah.
Cool. All right. So will conductivity increase or decrease? It will decrease because we have fewer ions. Ions conduct electricity in solution. Why would the volume of water not be an acceptable answer for question 1D? So that is this one here, our sulfuric acid, barium hydroxide, barium sulfate, and water. Why could we not do the volume of water?
Because it was already water.
Because there is already water, yes? If this is our reaction vessel, right? We have tons of H2O. H2O is the solvent. And in here we've got Ba2 plus ions, we've got OH minus ions, we've got H plus ions, and we've got SO4 2 minus ions. When it reacts, you end up with a few extra water molecules. Yes? And you end up with some BaSO4 solid down at the bottom. But the volume of water stays unchanged, essentially. I mean, it'll change a tiny bit, but not enough to measure. Does not change significantly. That makes sense? Good stuff. Why would the concentration of copper metal, concentration of CuS, not be an acceptable answer for number 1A?
It's considered mixed.
Because solids do not have concentrations, or you can say solids have consistent concentrations. i.e., and if you're wondering what IE stands for, it stands for the Latin id est. Id is that. Est is. So we're saying that is. In other words, that is to say. Or in other words. So anytime you see IE, it means in other words. Okay? I'm just letting you, you don't have to write all that down, but I just know that when I was in high school, people would write IE and QED and all sorts of things, and I never knew what they meant, right? So it's kind of nice to know an IE means in other words, okay? So solids do not have meaningful concentrations, i.e. the concentration cannot change, is unchangeable. Cannot change, so we ignore it. How are we feeling about that? Decent? Okay, good stuff. Any other questions on anything before we move on to new material? Okay. In that case, we are going to move on to 1.2a, which is on page 29. Uh-oh.
Collision field.
Okay, and we need to watch this little video on how to speed up chemical reactions and get a date. And honestly, this entire worksheet can be summed up in the 4 minutes and 55 seconds of this video. So pay good attention and feel free to watch it again later if you need to refresh for yourself. All right, here we go. Wake up. And we're going to press pause because I need to plug this in and we need to make it bigger. There we go. All right. And let's put on our subtitles. There we go. Ooh, that's quiet. Let's make that louder.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur.
Okay, we need to make this louder. This is going to be annoying. I'm so sorry.
More quickly.
There we go. Okay.
Meet our chemist, Harriet. She has a chemical reaction that needs to occur more quickly. Our chemist has some processes at her disposal that can help her speed up her reaction, and she knows of 5 ways. And to remember them, she thinks back to her days as a high school student, and the day she got a date for the dance. Harriet was in high school studying between classes. She had lost track of time and was going to be late to class. Unbeknownst to her, Harold, who was just around the corner, was running late too. They both sprinted to class, and as it happened, sprinted directly into one another. Now, this was no small collision. They ran squarely into one another in such a way that he knocked the books right out of her hand. "I'm sorry," he said. "Let me help you with your books." He kindly helped her recollect her belongings and politely offered to walk her to class. And you'll never guess who went together to the dance later that year. Yep, those two. So as we can see from this example, the key to getting a date for the dance is to collide with someone and knock the books out of their hands. Now, you're probably already aware that not all collisions lead to dates for the dance, thankfully. The collisions must have two important characteristics. One, correct orientation that allows books to be knocked from one's hands, and two, enough energy to knock the books out. Shortly after this incident, Harriet decided to tell me, her chemistry teacher, all about it. I noticed some interesting parallels between her story and chemical reaction rates, which happened to be what she was studying in the hallway the day of the collision. Together, we decided to set out on 2 missions. Harriet wanted to help all chemistry students and chemists remember how to speed up the rate of chemical reactions, and I, being the nice guy that I am, decided to make it my mission to help create educational environments in which more book-dropping collisions can take place to increase future chemists' chances of getting a date for the dance. In order to facilitate this improved dance date-getting process, I propose 5 changes to all schools that parallel Harriet's 5 ways to increase chemical reaction rates. First, I propose that we shrink the size of the hallways. This will make it more difficult to safely navigate the hallways and will cause more collisions than in larger hallways. And by increasing the number of collisions, we increase the likelihood that some of those collisions will have the correct alignment and enough energy to create a date to the dance. Now, chemically speaking, this is equivalent to lowering the volume of a reaction vessel or a reaction mixture. In doing so, the individual particles are closer together and more collisions will occur. More collisions means a greater likelihood that collisions with the appropriate energy and configuration will happen. Second, I propose increasing the overall population of the school. More students equals more collisions. By increasing the number of particles available for collision, we create an environment where more collisions can take place. Third, we must reduce the time allowed between classes. Heck, let's just cut it in half. In doing so, students will need to move more quickly to get from one class to the next. This increase in velocity will help make sure collisions have the appropriate amount of energy necessary to ensure book dropping. This is analogous to increasing the temperature of the reaction mixture. Higher temperature means particles are moving faster. Faster moving particles means more energy and a greater likelihood of reaction causing collision. Fourth, students must stop traveling in packs. By traveling in packs, those students on the outside of the pack insulate those in the middle from undergoing any collisions. By splitting up, each student has more area exposed that is available for a collision from a passing student. When particles travel in packs, the surface area is very small and only the outside particles can collide. However, by breaking up the clumps into individual particles, the total surface area is increased and each particle has an exposed surface that can react. Fifth, and finally, we hire a matchmaker. Is this colliding and book dropping too violent? Is there an easier way to get a date that requires less initial energy? Then a matchmaker will help with this. The matchmaker makes it easier for a couple to get together by coordinating the match. Our matchmaker is like a catalyst. Chemical catalysts function by lowering the activation energy. In other words, by lowering the energy required to start a reaction. They do this by bringing 2 particles together and orienting them correctly in space so that the 2 can meet at the correct configuration and allow a reaction to take place. So, to sum up, if a future chemist wants a date for the dance, he must collide with another person and knock the books out of their hands. And if a chemist wants to make a chemical reaction occur, the particles must collide in the correct orientation with an appropriate amount of energy. And both of these processes can be accelerated using the 5 methods I've described.
Okay, so that is all of today's lesson in 5 minutes. Okay?
I know.
That's it.
The rest of it is practice.
So what we're going to do is we're going to take a look a little bit more in depth at that. So we are on page 29.
Yeah, wasn't this like briefly explained kind of that?
Probably. Yeah. But I imagine you've forgotten a lot from Science 10, so. Collision theory. Collision theory states, for a reaction to occur, particles must first collide. This is the basic premise of collision theory. This is something that you could be asked to write a definition for. So the basic premise of collision theory, you could be asked for the definition. Now, what is a premise? A premise is the basic idea, okay? Well, it's not really a definition, but yeah. You could be asked for the basic premise. So for a reaction to occur, the particles have to collide. For those students to get a date, they have to collide. That's the basic idea. Now, there's extra stuff. What did they have to do? They didn't just have to collide, they had to collide with a certain amount of energy, and they had to collide with the right orientation, okay? So you need to have the correct geometry or orientation or alignment. So the words geometry, orientation, alignment, any of those can be used. Most often in chemistry, we use the word geometry. I don't know why. Orientation is sort of like sounds a little more, user-friendly, but whatever. And you have to collide with sufficient energy. And again, that word sufficient, instead of using the word sufficient, what's another word you could use? Enough. And so this is for a collision to be successful. So a successful collision can also be called an effective collision. So a successful collision is an effective collision. Those are collisions that result in a reaction. Now, before we move on, I will tell you that every year someone tells me that for a collision to be successful, it must have enough sufficient energy. I want you to think about what that means. If you say it has enough sufficient energy, what are you really saying? You're saying it has enough energy. So please try not to say that because it makes you sound a little ignorant. Do you know what I mean? But somebody's going to say it because it happens every year, even though I say this every year. So if it's you, don't be embarrassed. You're in good company. All through the years, all through my 30 years, somebody says it, okay? So not enough sufficient energy. Because that means enough energy. There are two ways to make the rate faster. And that is either by increasing the frequency of the reactions, of the collisions, or secondly, by increasing the energy of the collisions. If you increase the overall energy of collisions, you will increase the percentage of collisions which are successful. So energy of collisions increases the percent of collisions that are successful. And the frequency of collisions is just an increase in the number of collisions.
What is COL? Oh,
Yeah, COLLNS, collisions. Anytime something ends in ION, very often I'll just have the first part of the word with a little N up at the top. But thank you for asking. Anytime I do something like that and you don't know what it means, please ask. So there are 6 factors that can change either the frequency of the collisions or the energy of the collisions. Or both. So the first one is the concentration of the reactants. Okay, so we've got concentration. We have pressure, which relates to the volume, but that has to be for a, what type of reactant would you have? It would have to be a gas because you can't change the pressure of a liquid or a solid. You can change the temperature. You can change the surface area, and that is for heterogeneous reactions only. We'll talk about what that means in a moment. What does the prefix hetero mean? 2 or more, it means different. Okay, so hetero means different. So it means you have to have different areas that can have a surface in between them, right? If I have this liquid and that liquid and I pour them together, is there a surface between them? No. Okay, but if I dump this binder clip into the water, is there a surface between the binder clip and the water? Yes. Okay, so you have to have 2 areas that are different, heterogeneous, in order for surface area to be a factor. We'll talk more about that later. Okay. Catalyst. What's a catalyst? Tell your neighbor, what is a catalyst?
The big reactions take less energy.
A catalyst speeds up a reaction by making the reaction require less energy. And then this is one that they did not mention on the video. They only mentioned those 5. And that's because those first 5 are the ones you can change. Okay? You can change these. Any reaction, you can change these 5 things or 4 things if it's not a heterogeneous reaction. You can change these 5. But the nature of the reactants, they are what they are. They are either more prone to react or less prone to react just because of who they are. If you take sodium and you throw it into water, it will go bang. Okay? It goes bubble, 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 bang. If you take iron and you throw it into water, it will sit there and do not much of anything until it rusts, but that could take days, weeks, months. Yes? So it just depends on what the metal is, how fast it's going to react. That's what we call the nature of the reactants. You cannot change that for a given reaction. You can only compare this reaction with that reaction. Some of them will go faster just because, for example, sodium is really wanting to give away its electrons. Iron, not as much. Okay, So let us take a look first at concentration. So if we look at this, if you increase the aqueous concentration, that increases the number of collisions. I think that just makes sense, right? No one needs that explained, which increases the reaction rate. So you are increasing the frequency of collisions. Are you increasing the percentage of collisions which will be successful? Are you changing the percentage which have the correct orientation and enough energy? Remember, successful means have the correct geometry and sufficient energy. And the answer is no, we're not. You would have to make the particles move faster for, yeah, exactly, for those particles to have more energy, to collide with more energy. So if we had, at a low concentration, let's say at a low concentration, we had 100 collisions. And let's say that 80% of those were effective collisions. 80% were successful. How many successful collisions would you get? You would get 80 successful collisions. If we have a high concentration and we had 200 collisions, because we've, say, doubled the concentration or something like that, and 80% are still successful, how many successful collisions would that give us in total? That would give us 160 successful collisions. Okay, so concentration affects the frequency of collisions, but not the percent which are successful. It does not affect the energy of the collisions. Concentration does not change energy of collisions. We good with that? Okay. Pressure volume, very, very similar to concentration, but just for gases. Whoa, that was crazy. Sorry. I accidentally wrote on my master copy, so that's why there's all this writing already. Okay. So if we decrease the volume, what's happening to the pressure? Here we're decreasing volume. Pressure is going to increase. So anytime we decrease volume, if we decrease volume, pressure Increases. And if pressure increases, will we have more collisions or fewer collisions? We will have more collisions. Okay, so we'll have more collisions here. Here we will have fewer collisions. Will there be a change in the energy of those collisions? No, we're not changing the temperature, so there's no change in the energy of the collisions. And therefore, there is no change in the percentage of collisions which are successful. So pressure or volume works very much like concentration. Yep. We good? Cool. All right. So this is just another picture. I liked this picture because it kind of showed the particles moving around a little bit more. But pressure and volume, I've also noted here that it only works for gases because solids and liquids are not compressible. So if you want to make that note, you can.
Pressure and volume, right?
Pressure and volume, P and V. Now you can change the pressure a different way. You can change the overall pressure by adding an inert gas. Do you guys know what the word inert means? Inert means unreactive. So essentially you're making it so there are more particles in the container, but you've only added unreactive particles. You haven't changed the number of reactive particles. And unreactive particles, those would be your noble gases. They already have a full valence shell, so they do not need to react to become stable. Whoa, stop. Yeah. So before we have P1, okay, that's pressure number 1. And over here we have P2. And this little guy, these are inert gases, okay, the little black ones. And they also move around the container, all right? Off they go, bashing into walls, all right, bashing into other molecules, stuff like that. So is P2 greater than, less than, or equal to P1? Tell your partner, what do you think? P2, greater than, less than, or equal to P1? So we're going to vote greater than, or you can do thumbs up, greater than, less than, or equal to. P2 is 5, 4, 3, 2, vote. Yeah, P2 is greater than P1 because you have more particles bashing into the side of the container. Pressure is a measure of how much bashing there is on a certain area. So P2 is greater than P1. Are we going to get, so there will actually be more particle collisions in this thing, but will there be more particle collisions between reactive molecules? No. Okay, there's more overall collisions, but a lot of those collisions are between unreactive particles or between an unreactive particle and a reactive particle, and those don't contribute to the reaction rate. Okay? I don't know why I've drawn this. It's the same thing as above. So let's get rid of that. There we go. So, we good with that? We feel all right with that? So adding an inert gas, what does it do to the rate? Tell your partner, what does adding an inert gas do to the rate?
If you increase pressure, rate increases. So it increases, so rate does not change. It says it right there.
But why?
Because there's you're decreasing because no gas don't react. Yeah, so it's gonna be like but you go back to the bottom where it says neither changes, how should you rate it? Yeah.
Okay, again, we're going to vote. Does it increase rate, decrease rate, or stay the same? 5, 4, 3, 2, vote. I got some stays the same, stays the same. Yeah, it stays the same because there are no extra reactive particle collisions, okay? BW, can we guess what that means? Between. Is good? So there's more collisions, but a lot of them are like, you know, if I needed reactions between expo pens, yes, whiteboard pens, they would need to collide with other whiteboard pens. If I put, you know, my tablet pen in the mix, I'm going to end up with more collisions, but are these going to be effective? No, because these two won't react. These guys could react and maybe switch caps or something like that, yes. But the way the tablet pen doesn't have a cap, so it's useless, okay? So that's what goes on there. So pressure, increasing pressure will increase rate, but that's only if you increase pressure by decreasing volume. So if you increase pressure by decreasing volume, the rate increases. Because you get more collisions. Okay, good stuff. You need to be able to explain that. Yes, all of these things you need to be able to explain. Yes? So this is where it starts to get a little conceptual. You need to be able to say, this change makes a change in the frequency of collisions, or this change makes a change in the percentage of collisions which are successful. And this is why.
Quiz on Monday is just about.
Quiz on Monday has nothing to do with this. This is section 1.2. Okay? We'll give you some time to process this, think about it, all of that. Now, temperature is our fun one because temperature changes everything, because temperature makes particles move faster. Now, let's imagine that we cleared all the furniture out of this room, yes? And then I blindfolded you all, yes? And then I said, please walk slowly around the room, okay? You would collide with one another every once in a while, yeah? And then I said, okay, stop walking slowly. Now everybody run around the room. Would you collide more frequently? Yes. Would you collide with more energy?
Yeah.
Imagine you're running. You're going to collide with more energy than if you're moving slowly. Yes? So increasing temperature increases the number of collisions, and it increases the percentage of collisions which are successful. It does both. It's the only one that does both. So perhaps at low temperature, we have these particles, but they're moving slowly, okay? The size of the arrow is really small. You can see over on the right-hand side, they are moving very fast. Yes? These ones are like, la, la, la. Slowly wandering about, okay? So at a low temperature, we have fewer collisions. And we have lower energy collisions. And if the collisions are lower energy, that means we will have a smaller percent of collisions which are successful. At a high temp, particles are moving faster. Oh, I guess we should write over here the particles move slower. So at a high temp, number one, we get more collisions. And they are higher energy collisions. So we get a higher percentage of collisions which are There was another word that we used for successful. Do you remember what it was? Starts with an E. Effective, yes. That means the same as successful. So temperature does both. Increases the frequency, increases the percent which are successful. Now, this is something that you should memorize if you don't already know it. Temperature is literally a measure of the average kinetic energy of the particles. And kinetic energy is the energy of kinetic energy is moving energy. Okay, so kinetic energy is the energy of motion. So when you increase temperature, the kinetic energy increases, so the particles move faster. Okay, and kinetic energy can be abbreviated KE. So they collide more frequently, therefore the rate increases. They collide with more energy. And if they collide with more energy, a larger percent of collisions have sufficient energy to react. So they're not colliding and then the books are staying in their hands. They are smacking into each other and the books go flying. Yes? This, with the stars, part of a good explanation. So at a low temperature, maybe we have 10 collisions and 40% of them are successful. So we end up with 4 successful collisions. Maybe at a high temperature, we get 100 collisions and 80% of them are successful. So we will end up with 80 successful collisions. Does that make sense? So both of those are increasing. Anyone have any questions so far? Alrighty. Sorry, I'm just giving people a chance to copy it down if they want to. Surface area. Surface area increases the number of collisions. Okay, the frequency of collisions. And it works only for heterogeneous reactions. So most often it is going to involve a solid because solids are things that have very obvious surfaces, yes? And if you chop up the solid, you will then have a bigger surface, yes? So here we have a cube, and let's say that it is 2 centimeters on each side. We got a 2 by 2 by 2 centimeter cubed. So each side would have an area so the area is equal to, of a side, is 4 centimeters cubed. And that means that the area of 6 sides is equal to 4 times, centimeters squared times 6, which is 24 centimeters squared. Okay, so that is the surface area of the 2 centimeter by 2 centimeter by 2 centimeter cubed. Now, if we chop that up and we chop it up into 1 centimeter by 1 centimeter cubes, each side, the area of a side, is 1 centimeter cubed. And each cube has 6 sides, so 6 centimeter cubed is the area of 1 cube. Whoops, cube. But we don't just have 1 cube when we chop it up, we get 8 cubes. So we have 8 cubes, each at 6 centimeters squared, which gives you 48 centimeters squared. Do you need all of these numbers? Not really. What you need to know is that this number over here is smaller than that number over there. So if you chop something up, the surface area becomes bigger. So more of the surface is exposed. So if you have more surface exposed, will you end up with more frequent or less frequent collisions, or the same frequency? More frequent. Will those collisions be more energetic, less energetic, or the same? They will be the same amount of energy. There is no change to the energy of collisions. In fact, nothing changes the energy of collisions except for temperature. Okay? Only temperature changes the energy of the collisions. And we need to talk about the word phase. Lots of people hear the word phase and they think state, and they are related. Okay, so solid, liquid, gas, aqueous. It's possible that those are phases, but it is also possible that they are not different phases. A phase is an area in a system with different properties. So different phases are areas in the system with different properties. If I take this beaker here, which has some stuff in it, because I haven't cleaned it yet, okay? There are different phases in there because there's some junk floating around, but we're going to pretend there's no junk, yes? If I mix these two together, are there different phases? No. Were they different things though? Yes, but I put them together. So I had aqueous and I had aqueous, but they're not different phases because they're all just mixed together, okay? If you have a gas and a gas, are those going to be different phases or are they going to be the same phase? Same phase. Now, it is possible, can anyone think of two liquids that you could mix together and have them be in different phases?
Oil.
Oil and water. Okay, oil and water would give you different phases.
Because the density is different.
It's because not only is the density different, but water is a polar molecule, so it attaches to itself very strongly. And oil is nonpolar, so it doesn't have those positive and negative ends to interact with the water in the same way. So the water essentially excludes the oil from mixing, okay? So if you have heterogeneous reaction, you have things in different phases with a surface between them. And as I said before, most often that involves a solid. If you have a homogeneous reaction, all the reactants are going to be in the same phase. All the particles are mixed thoroughly and evenly. All right, so how can you have something that is heterogeneous? You can have a solid and a solid because this is a solid, this is a solid. Are those homogeneous? Are they the same as each other? No. So it doesn't matter that you have solid and solid. They will have a surface between them. Okay? You can have your solid and your liquid. Is there a surface between them?
Yeah.
Is there a surface? Yeah, the solid has a surface. Yeah, solid has a surface. The water only touches the solid at its surface. It does not touch the inside of the solid. Does that make sense? Yeah. Solid and gas have a surface. Solid and aqueous have a surface. Liquid and gas, surface. Aqueous and gas, surface. Liquid and liquid, but only if they're immiscible, and that means if they're unmixed. So this would be like oil and water. How often are you going to get that in chemistry 12? Pretty much never. Okay? Homogeneous. You can have liquid and aqueous because if you have something dissolved in water, it is with the liquid water. There's no surface between them. It's all just mixed. Okay, you can have aqueous and aqueous. The aqueous sodium is mixed with the aqueous chloride. You can have gas and gas. You can have liquid and liquid if miscible. So that would be like alcohol and water. Those mix. Okay. Phase A, phase B, I don't know that we need that. We're not going to have time to talk about catalysts today because they deserve their own little talk. Yeah, I think we're good. Yeah. So, homework. There's the purple homework, the blue homework, and the red homework.
What?
Purple homework is in the green book, and it is review for your quiz. Do you need to do all of it? No, you need to do as much as you need to do to feel like you totally understand and could answer questions on the quiz. Tab-din is also for the quiz. It's that one where I gave you the wrong page number the other day. I said page 6, number 3. It's supposed to be page 3, number 6. Okay? New stuff, pages 37 and 38. Again, that's in the green book. That's all going to be on Teams, but feel free to go get your phone and take a picture if you want to. Okay?
Yeah.
Yes.
I have to go to
Sorry.